Okay. All righty. Okay, we're good to roll. So good morning, everybody, and welcome to the fourth of our live lab walkthrough events. We are joined today by Ahmed Soliman, an associate professor in the Department of Building, Civil and Environmental Engineering, who specializes in green and smart constructional materials. I'll quickly pass it over, since we started a little bit late. Thanks for your patience. I'll quickly pass it over to Dr. Soliman. Over to you to introduce yourself.
Okay, look here. Okay, hello everyone, and welcome to my lab. My name is Ahmed Soliman, and I'm associate professor here at the Building, Civil and Environmental Department. Today we are going to talk about what we are doing in the lab, and actually we are dealing with one of the most used construction material worldwide, which will be the concrete. Okay, so let us start by giving like a brief introduction about the concrete, and let us ask like, what is the recipe for concrete? As you can see here, we have cement, we have water, we have aggregate, which can be fine and coarse. Once we start mixing the water and cement, we are going to have the binding material, which is going to hold aggregate with each other. And as you can see here, this cross section showing the aggregate piece, and between them is the binding material or the paste, which is going to hold and forming the body for our concrete. If we would like to improve the properties of our concrete, we can use some kind of chemical admixtures. For example, this one will accelerate the strength again, increase freeze and thaw resistance for our concrete. Or we can add supplement cementitious material types. This actually like industrial byproducts. For example, we have the slag coming out from iron production, we have fly ash, we have the silica fume, and we have other types which it can be natural, like volcanic ash. One of the main challenges that we face with concrete, that concrete has very low tensile strength. Therefore, we can start adding fibers, and as you can see here, we have different types of fibers actually is going to over or bridge the cracks, and therefore will delay the propagation for different for cracks, and consequently will improve the performance or tensile and flexion performance for our concrete. Okay, this like as a basic for concrete, and what we are doing here in our lab, that we try to produce sustainable, smart concrete. So let's start by the first part, which is sustainable. Actually, cement production can be considered as one of the main problems that we are facing. Why? Because it contributes with about 5 to 7% of the global carbon emission. Therefore, we would like to reduce the amount of cement. How we can do that? Simply, we can start replacing high portion from the cement by supplement cementitious material. Nowadays, we are working in our lab on what we call alternative binding material, like alkali activated material. This actually we try to activate such kind of supplement cementitious material, or we can call it in more precise way, alumina silicate material with activators, and therefore we can produce zero cement, concrete without cement, okay? Because once we activate this, we will have a material that's going to perform the same way like cement when we mix it with water. And this opened the way for us to implement different types of waste. For example, we have here the red mud, which is coming, as you know, from aluminum production. We can use it. The other way that we try to do by replacing the aggregate. And as you can see here, we have the agri waste, which actually agriculture waste, different types and different sizes. And we try to implement it inside our concrete. And as a result, we have here this, which we called agro-concrete. You can see here the agri-waste particles and also the natural aggregate that had been used. Other than that, we can have also rubber. We can add it like this tire rubber, which is one of the main problems. We start cutting it small, and therefore we can insert it inside our concrete. And it's known that this one will increase the impact resistance for our concrete. We have also here this very lightweight expanded glass, which we form it from glass waste. And this will result in producing what we call it lightweight concrete. As a more advanced, we start burning the agriculture waste to have what we call the biochar. Biochar is characterized by its ability to sequestrate carbon dioxide, and therefore it's not only can absorb and store carbon dioxide inside your concrete. Other than that, we have also here, we have a recent project that we are working on. We still in the primary stage, with or reuse the masks inside that we use due to COVID inside the concrete. We take it out to steel parts to be the fiber, or use itself by cutting it to pieces and use inside the concrete to act as a fiber reinforcement. Okay, so that's a way, like, as a general idea about having sustainable concrete by reducing the carbon impact and also its environmental impact. Moving to the smart kind, we have here a project where we start using phase change material. Phase change material is a new material. This material can absorb and release heat, and as it go from the liquid to the solid form, and from solid form to the liquid form, based on changing the temperature. It's not new technique, and as you can see here, Concordia had this model in 1983, okay, which has been done by Dr. Feldman, okay, to use this one to store heat storage model. And therefore, we are going to have a comfort zone inside the building for occupants, and also reduce the energy required to have an adequate environment. The new point that we are trying to do, how we can implement it inside the concrete. And this is one of the main challenges that we're trying to do it. Okay, therefore we'll have elements of concrete which will have this possibility of absorb and release heat based on the changing in the temperature. And I'm also going to share with you some of the products that we try to do here in our lab to serve our community, because we have to have some rationale about what we are doing. So one of them, I will start by this corner. We have this, which we call it anti. One of my master students, Mohammed al-Makadmi. The idea why was to use this pervious concrete. Pervious concrete, actually, when you pour water, you can see it's coming down, okay? So he thought about, okay, what if we try to use a heater, and this heat can be from regular electricity or by connecting it to the solar system. And as you can see, this little movie where he show when he add the snow on the surface, how it's going to melt and go down. So like this snow, and by heating it or connecting to electricity, they go. So the main point was to increase the connectivity for our concrete, and also the ability to transfer this heat. So this way, like, you will be safe to go during winter. Don't worry about the black ice. Here we have another product which is done with Ms. Diba and Muhammad also. We try to produce units from agriculture waste. This is the original one that you can find it in the market, okay? But here, this one, we produce it with 100% or approximately 100% waste. We use the agriculture waste. We use the new binding material, which is zero cement, and even the water. We used the wastewater effluent coming from paper production to activate it. And as you can see, we have different products come. Moving to the third one, which is actually like trying to produce sensible or piezoelectric material. Actually, we would like our concrete to produce electricity based on movement or mechanical performance. And this, as you can see, we tried first. This is the first model for the concrete, and another model here where we start adding red mud to add the sustainability dimension. And this, as you can see here in this one, we can use it in the parking lot. When the car park, it's going to use mechanical force. It gives light that this one occupied already. When it moves, it releases it. So give another signal and it will be free. So this, like, this general idea about what are we doing. Now, if we would like to talk about what exactly the steps that we follow when we start having our material. When we get our material, as you can see in the back, we start storing our material into different categories. We have the aggregate, we have the cement, we have the fiber, we have the admixtures. Then we start thinking about what will be a useful application for our material. Then we have experimental design, start making some trial batches, and fabricate small samples like that. This is small sample. We use it for measuring shrink here. So we put it down here. The and how the length of this element will change with time. And also we have other samples like cylinders and cube to evaluate the mechanical properties using the compression machine, for example, to test it, or the dynamic modulus. As you can see that all of these will try we have very harsh environment during winter. Even during summer, we have hot and dry. We use environmental chambers where we can simulate the actual condition that's happening outside. Therefore, we'll have a general idea about our material, what will be the performance inside the lab, and when we expose it outside during winter or during summer. And this will give us more confidence about what's our material and its performance. Therefore, we'll be sure that when we provide it or applied outside, it will give the desired performance.
I have a question about that, which is, I know one of the big problems with concrete as a sustainable material is how quickly it degrades under certain conditions. So does that also let you simulate the effects of time?
Yeah. So we have different tests. If you go to the to evaluate like, for example, we have here the RCPT test, or rapid chloride penetration test, where we start measuring how fast the chloride ions will go from one side to another. And this will give us indication, the potential for our reinforcement to corrode, and therefore we lose it. We have other tests, for example, the dynamic ultrasonic pulse velocity to detect any defects in our concrete. Also, we have our sample. When we have like standard tests, we can insert our samples, for example, in sulfate solution to simulate what's happening if we have attack by sulfate. And using the environmental chambers, we not exactly what's happening outside, but we have to accelerate it a little bit. So we expose it to more severe conditions than outside, inside the environmental chamber. And as you can see, the environmental chamber is programmed. You can change the temperature, you can change the relative humidity. Okay, I'm sorry, I can't turn it on because it will be noisy. Okay, but here, this environmental chamber, we have unit control that can control what's happening for your sample. Therefore, yes, we can simulate it, but we follow our protocols that we already are well known that this one will simulate what's happening. But instead of doing it in 100 days, we can do just in few months and we get the results. Okay, so as you can see, like here, even like we have some freezers similar to the one that you can have it in the kitchen, but this one is full with samples, and we already adjusted to very low temperature to simulate the cold condition. Okay, inside this room, like it's a little bit dark, but here, this also the environmental chamber. We can control the relative humidity and temperature inside, but a small one. If we go here inside this, we have here computer stations where students can sit down and start making analysis. We have the optical microscope if we would like to see what's happening inside our sample. We have the DSC, or diffraction scanning calorimetry, to have a thermal analysis for our sample. And this one can reach up to 1000 degrees. Like we are going to burn the sample to see exactly what are the components in our sample. And we have here the heat of hydration, which is going to measure how fast the hydration process or the chemical reaction between cement and water. Here we have this test, which we call it dynamic modulus, where we are going to induce pulse and measure how fast it's going through your sample. Therefore, you can detect if there is a crack, internal crack, or something like that. And this actually will give us an idea about the performance of our materials. Okay. So I know that you have many questions about sustainability.
Yes. I'd love to return actually to some of your aggregate tests and the materials you're working
Okay.
with. One of my main questions is kind of where specifically you're sourcing things from. Is there flexibility? Do you have a relationship with kind of local manufacturing or local agriculture?
Okay, for example, the agriculture waste we are getting, which in the research institution, okay, and it's well known for them. Just they are using it to dump it, or you can, and they use it for other application for feeding, for example. But the main point, like it will be, it depend, like, okay, they are posting that what will be the new potential for our waste. You have to approach them, saying them, we have a potential, not just you can use it as a feeding, we can use it in another product that will sustainable and will give you benefits.
And
so
can it be like any kind of plant material, or is it pretty specific?
Okay, some of them will work, some of them is not. And this actually we can say absolutely that all agricultural waste can be used. We have to make some tests. Some of them, for example, this one, when it absorbs water, it's going to expand and reduce the strength very significantly. Therefore, we try to use it in kind of application where we are not looking for strength, like control. Okay, some of them have this fibrous shape, so it can act like a fiber. And actually, we did like some tests, and they show very good resistance for shrinkage. So we can say absolutely that all the material can be used or recycled inside the concrete, but we have to think about the way that we are going to implement it. Okay, sometimes we need to make some treatment for it. For example, this rubber, you can use it direct, but it's not going to give you that performance if you start by pre-treating it with sodium hydroxide. It will increase the bond and will give you higher performance. Okay, so that's the main point, that you have to think about the application first. You have to characterize your material. So after we got our material, we start making physical and the chemical characterization. We may do X-ray, scan electron microscope to look for the microstructure. Then we select the application which most suit for this one. Then we make the trial samples, expose it to different environments, see the performance for our material. Is it going to work in harsh environment like winter, or we need to go back to the design stage and make some modification by adding fiber, adding some cementitious material, new admixtures, until we reach the point where we have a product that can survive outside.
I'm also curious about the kinds of fibers that you're using.
Here, for example, this one will be basalt fiber. Okay, we have nylon fibers. We have here this one, this, you see, like there is difference in the size and the type of the material. These plastic fibers, okay, these nylon fibers. The difference between all of them will be how much you are going to add. Each one will have the effect for on the tensile strength, but at the same time will affect the other properties. For example, if you add too much from this one, you are expecting to have harsh concrete, not flowable. Okay, if you add many fiber, it can make like this inside and maintain voids. Okay, so it's something like by trial, you have to do it. How much from this fiber will give you the desired. So you have to set first what are the required performance that you will be looking for, and based on that, you will be able to design your concrete to achieve the sustainability and performance level, because we can't just focus on sustainability. Okay, we have to have something sustainable and at the same time give us the required performance to be useful.
Does anyone ever work with repurposed textile waste? Because when you talk about plastic fibers or
there is a research, like there is research. You can search when you go online, we are not the only one doing this in the lab. The worldwide now, because it's one of the main concern. Okay, many research, even every day, like when I try to go for our journals, I find people start using something like, okay, I never thought about it. Okay, so we okay, what about this one? We tried, for example, this idea came to me like I just was walking out downstairs and find that bag from waste masks there. So I thought, why not we try? And actually, when I search online, I found already published paper, they tried and they proved it. So I have to think more advanced. What if we do it in another way? What if we use it with a different material, how we can achieve the required performance?
You work with other kind of repurposed construction materials. I know we have some of that here with the fiber and with the red mud, but I mean, I know that concrete itself is a big waste contaminant in landfills. Construction often deals
actually,
with
yeah, like the construction demolition waste, one of the main, I think it's represent 1/3 of the waste over production here in Canada. That's why we are now trying to make a new project where we would like to achieve a circular economy about waste, where we are going to go to the building, take out or demolish it, and reuse it or prepare a new product that can be reinstalled in the renovation for the building. Okay, and many technologies now that can be applied. For example, I'm working with art and science for a project using Mycelium, which is fungi. Use such kind of byproducts to produce like living material that can it's not like solid. You put low. It's going to grow with time until you have it, and it's going to improve the properties for your material.
Can you say more about that project?
Okay, we are still in the first stage, but as I said, like Mycelium, you know what? Like we got it from mushroom, and this one actually, when they try it, it's going to grow over the organic material and tied it with each other, and then with some techniques and some treatment, we can produce blocks. Okay, these blocks we can use it later on to build our building, and it's showing very good performance. The idea now that we try to do, how it is effective or not, this is going to meet our desire about construction material in the future or not. Is it going to survive in the environment? Because you know, like when you work with any living organism, the weather is going to have, like for example, is it going to level like in -35? Yes, we can survive with our coats, but for this material it will be that difficult. So this still, like I said, like in the primary stage, but we try to connect like how beauty we can do the material and at the same time have adequate performance.
You've mentioned a couple times this idea of the demands of performance, which I think relates to the kind of demands of architecture and urban planning and the built environment. So there's a way that your field is adapting itself to the needs of these other disciplines, but I'm curious if you also see your research kind of informing trends or decisions or policies that are adopted in those fields.
Okay, like it's hard to say like exactly, but for sure, like when you start making design, if you don't have in your mind that this one can be practically applied outside, okay, this will limit your imagination about like what you are going to do. Okay, but if you give them the tools, you start thinking with them, okay, we can provide you with such material that will perform well and you will meet your expectation. Okay, so that's the main point. As I said, like our rationale or the rationale for any work that we are doing will depend on the community, will depend on what they are looking for, how we make it safe. Okay, sustainability simply, we are saving our environment to the next generation. We're not doing to ourselves. Okay, so again, this is the main point. Like we have to have link between art, between chemistry, between material. Therefore, we can set with each other. Okay, identify the goals, identify what we are looking for. Each one will contribute based on his experience, and therefore will achieve like a good product. The time of having one side product already ended. Okay, you have to have a product that will meet sustainability, environmental requirements, material performance. So we can say that we are shifting to what we call integrated design, not single design.
But I also think that the available materials must also affect kind of perceptions of beauty and design in that way. Like I think about the early history of concrete and how its staining qualities, like just a sheet of concrete will eventually become stained and weathered, and how designers started bending over backwards trying to figure out ways around that. But then kind of a couple generations later, people began to perceive a weathered concrete wall in a brutalist building as something that was actually beautiful.
Yeah, actually, like if you go back to alkali activated material, the main idea is coming from back Egyptian ancient time when they built the pyramids. There is a say now that the alkali activated material they use it in the pyramids. The Romanic concrete, okay. So, but the main point will be what, as you mentioned, what are available, what are the waste. For example, here we are talking about agriculture waste. Maybe we are not facing that problem, but if you go to other agriculture countries, they are facing the problem significantly with this one. Industrial countries where they have a huge production from iron, they will have most with slag. If you go down in, I think like South America, like they have some problem with the fly ash itself. They have a huge amount. Red mud, one of the main problems that we still here in Canada and worldwide we are facing. So what is the material that that is available now, and what are the problems? This will act as a fuel for all researchers to start finding solution for it.
Yeah, I appreciate that you brought up the use of wastewater too, because I know that's kind of the other side, right? Not only in concrete production, but in so many industries, is these super water intensive methods, and how do you get the most out of it?
Yeah, actually, like for our concrete, for ready mix, after like in ready mix planet, when they wash the truck and they have this wastewater, before they don't know how they are going to use it. Now we have research already done. They start using that and to reduce the concrete, and they are now closing this loop, and that's very good. You have to think about reducing the waste coming from your side, and this will help you and will help the environment at the same time.
Another question we had was about when kind of talking through ideas of sustainability and longevity, we've looked at the material, but architecturally, what are the methods that are used to determine how green a building is, not only in its construction, but kind of in its output, in its energy?
Okay. If we talk about the building, is it going to be green or not? We have two main criteria. Operating energy. Operating energy will be related to lighting, will be the equipment, consumption for energy, the overall energy, like if you turn the air condition to have a comfort zone. On the other hand, we have the embodied energy, which will be the energy used to produce the material that you are going to form your building. Okay, so combination between them, this will be the resultant of the overall energy consumed by your operational energy. We are doing very well. Now when you go to buy any apparatus to your apartment, you find like this eco sign, means like it's very low in energy and they are grading. On the other side, in material, that's what we try. We have to reduce such kind of elements that can be implemented, that we can use it to fabricate your building, the total embodied energy. The second stage, as we mentioned here about phase change material, to have this material in your building to maintain the environment, reduce the energy loss, so you don't have to turn the heater again. And this will be the kind of overlapping between the design and the material science.
And I know some of the other ways you test out maybe a little more fun, and you talked about this concrete boat project that your students are kind of involved in that.
For Farsha, like we are talking about this complete canoe, and actually here this one, which is lightweight aggregate that we use it. Okay, and we have here also what we call it aerogel. If you read about it weighs nothing. Okay, so implementing such new materials inside your concrete in lighter weight, and therefore your concrete can float over. And you can just simply compare the weight for the coarse aggregate here, compare with the fine aggregate.
And you said again that was the ground up glass that you were trying to
Yes, expanded glass, yes.
And do you buy that? Do you acquire that already?
No, we have like different companies, even in Ontario, and they can provide us with this material because it's well known now. They start using even in the blocks, okay, to have lightweight blocks. So this material is available now.
Mm-hmm.
Yeah.
And is the concrete canoe tested out by floating, or is that?
Yeah, that's the main point. Like I was trying to get like a sample from concrete canoe to show you, but unfortunately we didn't have this time to arrange. Mm-hmm. Okay, because we spent a long time. Farshad helped me in cleaning the lab to have it, as you can see here. Okay, because you don't imagine like mixing concrete, we have a lot of dust coming out, and I think Farshad would show us how he can mix a few samples from just a sample for mortar. Okay, starting by mixing the cement, mixing the water, final product, which will be your aggregate or your concrete sample. Okay, Farshad, like if you can proceed.
Oh yeah, Farshad,
hi, my name is Farshad. I'm a graduate student under supervision of Dr. Soliman. I'm working on cementitious and non-cementitious material. We're looking for sustainability, as Dr. Soliman mentioned.
So Farshad already prepared a few amount of cement, and this will be the sand and the water. So we are going to do mortar. We are not going to do concrete. Mortar is cement, sand, which is a fine aggregate, and the water only. We are not going to add coarse, just to reduce the dust which will come here. We use this mixer. Quite dust. Yeah. Oh. Check now. Mm-hmm. Okay. Here, Farsha, can you get the cutters? You need to open.
I've heard about sand as sort of another ecological problem or material problem within concrete production, right? It has to be kind of specific.
Yeah, like we have a standard sand, but we now are shifting to what we call a performance-based design, where you are free to use whatever you are going to use with certain limits, like what will be the performance? Are you looking for strength? Are you looking for flowability? Whatever you're looking for this. So you are free. And this opened the way for us to use whatever material that we would like to use. The main guide would be the performance. What would be the performance? If I achieve the performance that I'm looking for, I'm free to do whatever I want. So that's why we care about using different temperature, relative humidity, simulate the summer, simulate the winter, just to be sure that our material will sustain when we implement it outside. And actually, we have like, I think like one of my students, he already took some concrete samples and just dumped it in his backyard for more than 2 years now. And this is like real field condition. And therefore, we can get like useful information about like, okay, what's the difference between maintaining inside the environmental chamber and even when we put it outside.
Yeah, it's interesting how solving all of these design problems also really becomes an exercise in the concrete becoming incredibly local and sources and materials.
Actually, like this one of the main reasons why the concrete is the most used construction material. Just you have the binding material, you mix it with the aggregate, you mix it, and aggregate, you are free to use coarse aggregate or you use fine aggregate, different types of waste, and therefore you will be able to reduce your concrete at the end.
Can folks hear me?
Yeah, we can hear you now.
Yeah. There are a couple of questions in the chat. I don't know if Louis, would you like to ask your question first? You can unmute yourself.
Sure. I would like to know, I think it was mentioned that the biochar could absorb CO2. And I was wondering how that like worked. Actually, like how does it absorb the CO2?
Okay, like
as a, yeah.
If you look about like, it's something like related to the material itself, and inside the biochar itself, like it has the ability to connect with the carbon dioxide, and therefore it can store it inside the voids, inside the aggregate itself that we are using it. So it's chemically connected with that.
And I'm sorry, can I ask if there's like a maximum absorption to the biochar of CO2?
Actually,
like
that's a very good question. Like the main point that after a while, the biochar will be saturated with the carbon dioxide. And that's exactly what we are working now on, how we make it refreshed to the biochar so it can continue absorbing from one time to another. But this one of the main challenge that when you add the biochar, is going to absorb carbon dioxide, reach the limit, and that's it. Okay. But this is not our desire. We would like to have it live, where it's going to absorb today and tomorrow, and after that, like we can have a way to recharge it. Therefore, it will be active again, and so on.
Thank you. Thank you. I have another question here from Joya. Go ahead, Joya.
Yes, so I was wondering, what are the advantages of making light concrete with aerogel?
Okay. Having light concrete itself is one of the main advantages. You can think about it like how you, if you have a block of concrete, if it's easy to move it from one place to another, okay, how many labors you will need, how many, the truck itself, you can increase the capacity, you can increase many things. So the weight of the concrete is one of the main limitations, like that affect how many labors for the construction process itself. So achieving very light, this will be one. The other thing, from the thermal point, okay, when you add aerogel, you are going to make your concrete like more as an isolation material, which is going to prevent loss of moisture, loss of thermal and heat. So this will be the benefit also. So we have two things. First will be the weight of the material itself. And as you can see, like, I don't know, like the camera is not here, but if we have this block, okay, the camera, when it comes here, this block, okay, we use it, for example, agriculture waste, which is light material. Now it's very easy to carry it. Compare with the other block, if we have the same block with concrete, for example, the cylinder there, it's way heavier than this one. So two things will affect. First, will be having light concrete will be easy to handle it, easy to cast, will reduce the total load. As have to make your element to carry amount of load when the dead load for the concrete itself represent huge portion. So if you reduce it, you have more, you will have a smaller foundation. You will not be aware about or worried about the soil itself and the bearing capacity for the soil. And at the same time, you will have good thermal performance for your concrete. Okay.
I have another question about the piezoelectric concrete, which is, you know, I see in these kind of graphics that there's a theoretical application for using the weight and pressure of a car to produce that electricity, but I also see this diagram of people running. And what are the kind of parameters of that? Like, how sensitive can this be, and what are the kind of energy outputs that would?
Okay, like, you know, here, like, we can make the running tracks where people is going to go over it. Once you press, you are inducing mechanical deformation or deform your sample. This piezoelectric will absorb or generate electricity before you can supply it later on. Okay. How sensitive is this one? Actually, like in German, they produce already unit where for floors you can to store energy. Yes, it's not that much. Okay, but as a new technology, I think it will have a future.
And is it limited by weather conditions as well? Like, I imagine that it could be easily corroded if there's water or.
Okay, like this will be the final product shape. Like you can make it sealed, but you have to maintain the the ability to move. Once it moves, it's going to store or generate electricity. Other than that, we can protect. Like I think the product that they have it now in German, it's totally sealed and it's outside. Okay, and I think like the mechanical movement, like if you have a spring, okay, you can press on it. Sorry for that. During summer or during winter, it's going to deform the same distance under loads. So yes, again, this will be one parameter that we used or we included during our experimental design. And yes, it's still, we're doing work on it. So you are ready? So now we can move to Farshad. He's going to start mixing. He adds the sand, cement, and then he will add the water to form the binding material and our mortar. So this is just a simulation for how to make mortar. We're not following the exact standard, but just to show you what will be the final product when we have cement, aggregate, water. Okay, it's okay. So, yeah, one more. So we have like the American standard material, okay, STM, for casting or mixing mortar, mixing concrete, okay. And this actually like what we try to produce another standard for testing these different materials. Because once you add it, you will see that the performance is going to change. So this one of the main weakness point that we are facing now, that we don't have standards for the new material or material that include waste. Okay, you can imagine like here, this rubber, how this one is flexible compared to the solid one. Okay, therefore, the performance will be different. Phase change material contain paraffin, and this paraffin, once it comes in contact with cement, is going to stop the hydration and stop the strength again. So how we are going to deal with this problem? This another aspect. So behind each of these material, we have a science running to make it usable, and we can implement it in concrete to maintain the final product, which is very solid material that can sustain for longer time.
I wonder if we could ask
I
another.
forgot to mention for the fiber that we have also nano fibers, nanocarbon tubes, okay, that's going to be used. And actually the nanoscience in concrete, do you finish? Okay, just finish mix, then we go back to talk about the nanomaterial. Okay, this is the mold, standard mold. We are going to do it like 5 by 5, which will be, this will be the final product come. Okay. So we have a procedure for casting cubes where we are going to add 1/3, then compacted, then add the second one compacted, and so on. Okay, this is the compact rod that we are going to use.
And it produces one of these that here, these little cubes.
Yeah, these little cubes. This one is already tested, but this one, for example,
After you've tested it for strength and
not strength, durability.
okay.
We expose it to very humid and sulfated tag. So as you can see, like it start to be loose. Okay, so this one of the point, how we can, well, as you can see, like there's a number here, which mentioning like what is this sample. Okay, so now like after exposing it to weathering condition, it start to be loose. So we start, okay, this trial one, we have second trial to until we reach like adequate product at the end that will sustain the performance. Okay. You can see this is the regular concrete. It's very solid. You can do anything with it. Okay, so that's what we are looking for.
Pretty close to time. So I just wanted to thank you, Farshad, also you, Dr. Soliman, so much for sharing your work with us.
That's great. It was my pleasure.
It's very exciting to see everything that's going on in here.
Okay.
Yeah.
So like, as I said, like concrete is one of the most used construction material worldwide, and it will remain like that. Okay, people start saying, no, we are going to move to another material. But as far as we are working, as far as we are producing low carbon concrete, okay, it will remain. It's like long time knowledge that we can just dump it and start working with new. Like that's for sure. Like when you think now, when they went even to Mars, they are thinking about how they can produce concrete there. Okay, so if concrete is going to end, they never would thought about it. But now we are thinking about how we generate similar. Yes, maybe after quite a few time, like you are going to find new material. We're not going to use cement, we're not going to use such aggregate, but still we will have this word concrete in construction will be remain for a long time.
I wonder if we could ask a final question.
Yes.
Okay, wonderful. Anik, did you want to go ahead?
Hi, Dr. Soliman.
Hi, how are you?
Very good. It's a question going back on Joya's original question about the glass bricks. Through your tests, are the bricks made with glass aggregate just as strong as the heavier ones? And also, do all the construction waste only go back to the construction, or can they be repurposed for other everyday things?
Okay, like, is it going to be stronger or not?
Like just as strong as the
I think Nans Island, we have a bridge already built. Okay, if you are following the news, we have bridge. They built it with recycled glass as an aggregate. So yeah, it's going to this lightweight. Okay, if you compare it with the regular glass or the other type, it's going to change. It will be different. So it will depend. You're going to use glass for. If you are going to use it to achieve lightweight, this will be the product. If you are going to use it to produce concrete that will be working in a bridge, it will be different. Okay, you can see like from having this glass bottle here, this one, if you crush it down, you are going to have very fine, you will have a coarse, you will have different sizes. You can manufacture it again and do other process to change the properties for your glass. But at the end, it will depend on what is the application. Okay, selecting application will be one of the key point of selecting what will be the shape you are going to implement any type of this waste. Okay.
Wonderful. Thank you for that, Anik. I hope that answered your questions. I guess on that note, we will say an official goodbye. Thank you so much for inviting us into your lab.
Much.
It's been a pleasure. We appreciate you setting up all those samples for us to view and get a really better understanding of the materials that you work with. So audience members, students, Cecilia, everybody from Fourth Space and everybody in the lab, thanks so much for your time. And on that note, I'm going to close up the Zoom and we'll see you for our next episode. Bye, everybody.
Bye.